All right, well, welcome again, everybody, to Astronomy Daily Live. It's 2 hours UTC, and it's time for us once again to gather together in this circle of friends and sort of a virtual porch. Just sort of, kick back here, grab our favorite consumable of choice. I've got the uh, this is the hydrogen hydroxide again tonight. I've got a big, full mug of it there. So I've got at least 5,000 billion molecules in there. So yeah, just that'll do for a while. So cheers. And on the panel is Bobby. Hey there, Bobby. What's going on?
Nothing much. And it's kind of a bit messed up that KBC didn't make the trip tonight.
Ah,
Wolverine did.
okay. Cool. I was
And
rushing.
while KBC is a legitimate station, Wolverine's a pirate.
Oh, okay, cool. I always like those pirates. So yeah, I was rushing around a little bit here because the moon just rose, and it's pretty close to full moon. So it's always kind of nice. Took a couple of pictures with my smartphone, so maybe I'll post those up a little bit later. So I'm going to go over to the chat and say hi to Atta. Uh,
Hey, Ottawa.
yeah. Hey there, Atta. Nice to see
I don't
you in
think
the
you
chat.
did any rabbiting tonight.
No, you know what? I uh, I was working on some other things, and no, it just completely like that. I've
Yeah,
got
I was
to.
mostly focused on trying to see if I can get KBC, but that wasn't happening.
Okay. Yeah, I need to stick on that, and yeah, um, I've sort of officially changed it. Actually, I need to change it over on the Rabbit, but it is definitely going to be a Sunday midnight movie. So as long as I can remember, every Sunday at 0 hours UTC, I will be screening some kind of movie that's either sci-fi or science related or something like that. Uh, yeah, just some kind of either cheesy sci-fi from the 50s or the 60s or the 40s, or yeah, I can screen Cosmos, or I can screen The Secret Life of Machines. That's there. And yeah, if anybody has any suggestions, let me know, and I will consider it for sure. So cheers.
Here's Uncle Bill Durr in yellow.
Hey there, Uncle Bill. Nice to see you in the chat. So I got something else in the mail today that actually I wasn't expecting this until next week, but I got the notification that it was in my mailbox. So I'm like, okay, I'm going to run down to the mailbox and grab it. And it was in a little padded um, um, package, and I'm going to let me see what that comment was first in the chat before I. Tonight is pretty clear. Yeah, you know, Atta, it's the same here. I've got some high thin clouds, but actually it looks like it might be clearing up here, which might be a good thing because the thing I'm going to show you came in this cute little case here. All right, so I'm going to open this up. Hold on. So this is a focal reducer.
I can see you.
Does it go this way?
That's it's like an eyepiece or what?
What this does is it reduces the focal length of your device by a factor of 2. So what that will do, it sort of has 2 effects that are related. First is that, since it reduces the focal length by a factor of 2, it will reduce the magnification by a factor of 2. But what it also does, and the reason why I got it, is because what it will also do is it will increase my field of view, both width and height, by a factor of 2. So I'll actually have a wider field of view for my devices. And I actually pulled those out. I've got my webcam here. Hold on. So this is the modified webcam that I use to put onto that scope, so you folks can see, the moon and the planets and everything else. And this focal reducer just screws into the end there. I will demonstrate.
Dr. Water, you better have brought it for OPT telescopes.
You can see the chip in there, that little rectangle in there.
Yeah.
There it is.
And there is Mother Nature and Bob Dog.
Mother Nature, nice to see you again in the chat. Bob Dog, hope all is well up there in the Great White North. Anyway, so that goes on to my webcam. So that I was pretty sure was going to screw in okay, but and that's great, right? Because now I'll have a wider field of view. One of the problems, it's not really a problem, but sort of not optimum, is that I've got a really narrow field of view with this guy. I mean, the moon is like, I can see like 1/10 of the moon at once, right? So with this, I'll actually be able to see 1/5 of the moon at once, which is still not great, but it is much better. Now, the other device that I was hoping that this was going to fit onto is my CCD camera here. So this is an old school S-Big ST7 ST7ME. That. Can you see that? I've got to be careful how I hold this thing. Oh, it's backwards on my screen, but maybe it's right side on yours.
Yeah, ST-7ME.
7ME, yeah. So
Yeah.
this uses a parallel port. No USB here, boys and girls. So
Now, can you put a parallel to USB?
I probably can. Yeah. I don't really see.
Check the comment. Check the comment that Uncle Bill put.
Okay, let me pull up my chat here. Uncle Bill. Yep. Yeah. I've got this just to increase the field of view, as I said, both on the webcam, and what I was worried about was if it was going to fit into that. It was going to screw into my CCD camera. So watch, I will demonstrate, and we'll see if it actually fits.
Looks like Mother Nature didn't stay long and stuff. So if that's true, later, Mother Nature. Fitting pretty darn well.
Anyway, so to my surprise, that screws in there just fine. It's the same thread. So this is very, very cool. The only thing that I was warned about, and I'm not going to know until... Hello, puppy. I'm not going to know until I get this out on the sky, is whether that focal reducer is going to change sort of the position of the focus. I'm not quite sure. I'm going to go ahead and mute Bobby's doggy. There we go. But phase one is that it fits. It fits. So now, this whole thing will go into the bottom of the telescope like that, like normal, and we will see. We will see. So, as I mentioned, as I briefly mentioned, it might actually be clearing up here tonight. Hold on a sec. I always like to keep the dust caps on all of my things because I'm in a dusty environment. So the anything I can do to keep dust off the precious optics is really, really, really important. So let's see. Okay, yeah, Mother Nature just checked in, checked out. So glad you could stop by. Come in anytime you want. Anytime you want. So rainy up there, huh? Bob Dog? Yeah, bummer. That means not a clear sky. So yeah, this is very, very cool. And here, listen, it makes a little sound. Cool. So, and then I can put it back in its cute little case here, right, like that, and snap it shut, and it's protected from the dust. And then I can put my dust cap on my CCD camera, and yeehaw, yeehaw. So, yeah, very, very cool. Yeah, it's always a good idea, to keep the dust caps on your optics, because it just you don't want any dust. And what I'm doing, right, it's really, really important to have as nice, clean, and clear optics as I can possibly do. As you may recall, looking at my flat fields from my scope, I've got a lot of dust on them. Even so. So yeah, just absolutely amazing how that dust gets in there. But yeah, this and I guess I haven't showed this off in a little while, but I guess I can. Let's see. Let me take this apart a little bit. Hold on. So that top CCD is sort of the science CCD, and the bottom one there is actually the guiding CCD, which I'm still trying to figure out if I'm going to be able to use or not. We'll see. But yeah, this nose piece, just sort of unscrews, and then what you can't see is the filter wheel, and that's sort of this top part here. Hold on. And inside of there is a wheel that has, I think it's got like 5 positions. And right now it has a empty slot, which is what I've got it set to right now. It has I guess you'd call it a clear filter, which is just, actually I'm not sure if it's a clear or if it's a some kind of a lunar or glare filter. And then I've got an R and a G and a B, a red, green, and a blue filter. So these are very, very unscientific filters, but they are good enough. And as long as I have the spectral response for all of these filters, I can definitely do science with them. So it's not a big deal. But my testing right now doesn't require any kind of filtering. So I just have the open hole there. So you can sort of see the round part in front, and then there's a piece of glass in front of the CCD, and that sort of encloses the CCD in a cold environment. So this is thermoelectrically cooled, right? It's got a little fan in the back here to pull out the heat. Here's sort of a little bit of the insides there. You can see it. So yeah, this I can cool down really, really easily 30 degrees below ambient. And that's 30 degrees Celsius below ambient. So I can definitely usually get this below 0 Celsius, which is great. These kinds of electronics really, really like to be cold. So I try to make them as cold as I can without, this thing having to work really, really, really hard. So anyway, I was a little bit worried that this guy wasn't going to fit on either of them, and it turns out that it fits on both. So I'm pretty happy with that. And as I said, it might be actually clearing up tonight. So if it does, most likely I'm going to go out and I don't know if I'll do anything with the CCD, because then I'd have to drag out that computer back there, and it's like, I shouldn't be complaining, right? Because I don't have to go anywhere at all to have a completely black sky. Now, granted, the moon is out now, so of course it's not black. But I don't have to lug this stuff any further, than my front yard. And most people have to, pack their things in a car, and they have to drive, and they have to unpack, and then they have to, all that. I just have to carry all this right outside, but yeah, having to set all that up and everything else, it's like, well, if I'm not really going to be doing any science with this thing tonight, then I'm probably going to leave that until maybe another time. But if it does get clear, I will definitely be putting this on just the eyepiece I have for this, so I can sort of visually check it, and then I'll probably put it on the webcam too, and maybe if things look okay, maybe I'll live stream a little bit of that. Don't know. You know, if you haven't hit the notification bell yet, do so, because I think you'll be notified um, if I do that. So, cheers. I'm going to check up on the chat here. Make sure there's not too much mischief. Yeah. I totally agree, Uncle Bill. Minimize the glass if you can't. Yeah, well, Atta, I would say that you are on multiple learning curves, parallel ones, right? Because you're learning the sky and you're learning the instrumentation at the same time. So yeah, you sort of have a double whammy there, and you just need some clear sky so you can get some sky time.
There's hip to raptor, or I don't know how he does it.
Heptacular raptor.
Heptacular raptor. Okay.
Heptacular raptor is in the chat, and darkness is blinding. You know what I used to do? When I was just observing, right? I was observing like the Herschel list or the Messier objects or something. I had a pair of really dark sunglasses, right? Really dark. And before I would go out to observe, I would put those on and I would go sit in my dark closet for like 45 minutes, right? We're just in total blackness, right? With the shades on. And then when I wanted to go out, I would keep the shades on, and I would squint my eyes with the shades on, and I'd go outside, and then in the darkness I'd be able to open my eyes, but I would uh, wear my sunglasses at night. So what's his name? Corey. Who's the guy that sang that song, Sunglasses at Night? That's a real thing. Because I did it. I thought that was, like the astronomer's anthem song, right? It's nice to see you in the chat, Hip. And yeah, I just like to say once in a while, Heptacular Raptor. I think that's a fantastic game for sure. So cheers. I'm just loving this HOH tonight. Cheers. All right. Well, cool. Let's see. Where should we go tonight? As I say, the biggest problem I have is not to figure out. It's like, oh, I don't have anything to talk about or to look at. No, I've got the opposite problem, right? It's like there's so much. It's like what is the one or two things that we can sort of do? And you know, over on the Discord a couple of days ago, I posted a couple of articles. I'm gonna I'm gonna share my screen here. Whoop. Share my screen. Like that. I wonder why sometimes when it goes to infinity, it goes down the center. Sometimes it goes up like that. Sometimes it goes off to the side. I don't know why it does that. I don't know. Okay. Well, enough of that. Let's see. Let's go over to the Discord channel and oh, I just posted this over there too. Where did I put it? Here. I saw this on my Twitter feed. Right. The the orbit of the TESS spacecraft is such that every so often I forget it comes pretty close to Earth, close enough to actually be seen, right? So here it is. Here is the TESS spacecraft observed. When was this observed? August 25th at 1:34. So pretty much one day ago, or so, and magnitude 17.2. So that's, I mean, relatively speaking, that's pretty bright, right? And so what you're seeing here, of course, is they are tracking the spacecraft itself, and it is moving relative to the background stars. So that has an effect of us seeing the stars moving, right? So these are just star streaks here. And, star streaks, I think, are really, really cool because, I mean, well, one, you can obviously see that well, it's sort of obvious, I guess, that they were taking a bunch of short exposures and adding them up. You see how there's like these individual dots here. Let's see if I can zoom in on that a little bit more. They're almost like individual dots. Ding, 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 ding. So it looks like, they took a series of these shots and then added them up, right? Instead of taking a long exposure. Now, they're saying that it's just a four minute exposure. But that doesn't explain why I'm seeing, individual little dots. But one of the cool things too is that see how there's almost like these gaps where it sort of dims and then brightens again. So there's some interesting structure in there, and it's probably atmospheric, probably, scintillation, twinkling, right? But anyway, I think it's pretty cool that with a 0.41 meter telescope, which is a 16-inch telescope, they were able to see this pretty well. And actually, the tracking on that is really nice. You see how nice and round that is? But yeah, that is not an asteroid. That's not a star. That is a spacecraft. That is the TESS spacecraft. TESS is what does that stand for again? Is it going to say here? Oh, I don't know if it says it here. Oh, it doesn't say it here. I'm going to tweet that I'm live. I forgot to do that. So the Transiting Exoplanet Survey Satellite, right? So this is sort of the next generation of Kepler, right? I mean, it's going to be looking for exoplanets by watching them transit their stars, and we're going to watch the stars slightly dim during that time. So it's just an occultation. It's all it is. It's an occultation. of a planet going across the face of its star. But yeah, I thought that was pretty cool that we're going to be able to see that. And 17.2, 17.2 isn't is actually, I think I'm going to maybe be able to see that faint as well. So yeah, I mean, I would have to take a longer exposure, right? I'd have to take a longer exposure, but I may be able to see tests as well. So I don't know. I don't know. I mean, I would have to be able to track it, right? Um, so yeah, we'll see how that goes. Maybe I'll think about doing that. But yeah, I thought that was kind of cool. But anyway, I had posted up here a couple of papers. Let's see about these CubeSats and constellations of microsats. And this one actually caught my eye, and I haven't looked at the paper, so let's do that. I've got a pretty strong interest in near Earth objects as well, detecting them, and they have come up with sort of an interesting twist on this that I thought was interesting enough, although, as I said, I haven't read the paper. So let's sort of look at this, right? So um, uh, so in order to find approximately 90% of the near Earth objects that are 140 meters or larger, with the current existing technologies, right, it's going to take us 15 to 20 years to find 90% of them, right? So to find all of them, well, it I guess I would say it's almost impossible to find them all because we don't know how many there are. So we're not going to be able to find them all. But if we can find 90% of them, yeah, that might be good enough, right? But it's going to take a long time, right? Long time. And if you decrease that size, right, then it's even going to take longer, right? Decades and decades and decades. And the reason why is because these things are so faint, right? Um, they're and when they're really, really far away from us, they're extremely faint, right? When they're really, really near us, they're a little bit brighter, but they're still really, really faint, right? So our best chance to actually see these things right now is when they are near us. Well, that doesn't happen very often, right? I mean, it might happen once a year, right? Usually, more like, once every 2 years or 3 years, right? So, but what these guys have decided to do is to actually launch a constellation of microsatellites that are going to orbit the sun, right? They're going to be sort of in the same orbit as these objects. At least that's how I'm reading it, right? If these objects cross the Earth orbit inside the sun detected constellation, right, in orbit around the sun. So what they're saying is, I think, is that they're going to sort of send these microsatellites out to sort of encounter, not exactly encounter these objects, but at least get close enough to be able to see them. And I thought that was a pretty cool idea, right? Because that increases our chances of seeing them and reduces the amount of time it's going to take to find them all. So I thought that was very, very cool. And I'm kind of interested in seeing what they call a microsatellite. What size a satellite, what size a telescope they're actually talking about. Because, I mean, you're really, those of you who watched Skylius and Fraser the other day, right? You don't need a big telescope to see some pretty faint stuff. So that's pretty incredible, right? So that's primarily what I was interested in finding out, is just how big. Okay, well, okay. Well, here it is, right? So they're calling a microsatellite a satellite that has a 20 centimeter telescope. Well, do you know what a 20 centimeter telescope looks like? It looks just like that. That's a 20 centimeter telescope right there. So that's sort of the size of the telescope they're talking about. Hey, that is going to be big enough to definitely do what they want to do. So, all right, let me check my chat really quick.
Check the chat. Check the chat.
Check the chat. Check the chat. Oh, cool. Uncle Bill, have that person get a hold of me. You can give him my email, and yeah, let's do that. That sounds interesting. Sounds interesting. Cheers. Yeah, I think that is my understanding too. Let's continue looking at the paper here. I'll share my screen again. I just wanted to show you a microsatellite. Okay, here we go. So 20 centimeters. So they're just doing a simulation here, right? So it looks like they want to try to look down to 23rd magnitude. Wow. Okay. That's asking a lot for a 20 centimeter scope, but they are going to be in space, so it's going to be really dark, and it's never going to be cloudy, and there's no atmosphere to sort of blur things out. So I'll bet you that you gain at least a couple of magnitudes there. So yeah, with a long enough exposure, you might be able to see 23rd. Let's see. So a 23 magnitude object that's 140 meters across can be seen at 0.8 AU. Okay. Close enough to detect 3 months until they're no longer. What will be gained by placing second such telescope into operation? Okay. 15 times beyond the saturation. Okay, cool. Right. So yeah, they're looking for moving objects, of course. Long exposure. Okay. Yeah. Shift and add, that's a typical algorithm for that kind of stuff. Let's see. synthetic tracking is possible because modern CMOS focal plane sensors can be read out at very low read noise. Yeah, CMOS cameras are getting better and better and better compared to CCDs. They're still noisier than CCDs, but I'm thinking that maybe at some point they're going to be comparable and maybe even better. I don't know. And if you can read at video rates and work just as well as a CCD camera, not bad.
Some of the models call for deployment in pairs, so some duplicate sightings with parallax can be made. Uncle
Cool.
Bill.
Nice. Parallax, right? And if you can measure the parallax, you can know exactly how far away it is. And that's sweet. That is nice. Okay, so yeah, 20-second magnitude. Cool. I wonder if that's a typo. Microsats? I think that's supposed to be microsats, I think. So 10 square degrees, 20-second magnitude in 10 minutes. It's not too bad. It's nice to be able to simulate all these things first, before it's like, well, let's just make a wild guess. No. You check all this out first. Oh, okay. So case 1 was 8 satellites uniformly spaced around the sun. 20-second magnitude NEO is about 140 meters in diameter. Okay, all right, yeah. So the completion rate for single detections was extremely high after 8 years. Linked completion rate. Not quite sure what that term means. Not detect statistics for third category. Case 2 also had eight satellites, but 4 pairs. So the pairs were spaced. They need a D there. About 200,000 kilometers apart. Yeah, cool. Okay, so this improved our link detection stat from 75 to 80. All right. And case 3 had 12 satellites and 6 pairs. And they got up to 93%. Sweet. So let's see, we should explain the difference between the 3 detection, link detection, and orbit detection in a bit more detail. If a NEO is only detected once, we know its brightness, position, and velocity at one point in time. We don't know its orbit. Right. I mean, in order to know its orbit, you have to make several observations over as long of a period of time as you possibly can. But they're saying if 10 years later that NEO is detected again by somebody else, right, they're not going to be able to link the 2 observations together. Okay, so in some sense, an isolated detection of a NEO will result in the object being lost. The concept of a linked or cataloged observation is that there are now there's a sequence of measurements. Okay, cool, cool, right. So yeah, I mean, once they have an idea of the orbit, then even if they don't observe it for a while, if they know where it should be because they know its orbit, then they can go back and look where it's supposed to be and hopefully find it. True, 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 true. I mean, a few decades, yeah. Um, yeah. You just need a longer length of time to actually observe because yeah, the orbits aren't going to be all that great. Just a couple observations. Uh, so a 1% error in the semi-major axis means that the orbit period has an error of 1.5%. So yeah, I mean, over 10 years, you're looking at, quite a big error, and you may lose it. Uh, wow, and that's an arc that extends over one astronomical unit, which is a lot. Cool, very, very cool. Looks like they've worked a lot of this stuff out. Low sensitivity, doubling the number of telescopes will double the discovery rate, and decrease by a factor of 2 the time needed to find 90% of them. Yeah, cool. So yeah, they're just working out. It's like if we can do this, then this. But if we can improve things, even by a little bit, right? Increasing the sensitivity by one magnitude, um, you can see further out. So very cool. Yep. Increase the volume versus time. Uh, right is a single telescope in space configured to have a similar performance. Um, interesting. Pretty cool. Need to understand this. If 140 meter NEO were detectable out to 0.4 AU from Earth, and if their average velocity is 10 kilometers a second, they will typically be detectable for 50 days.
The chat.
Telescope. Check the chat. Okay. And survey the nighttime sky in 20 days. Then building another scope and doubling the sky coverage area would not double the rate of detection. I'm checking the chat on Discord. Looks, yeah, very, very thorough job. Getting funkier all the time. Funny.
You're killing me with kindness, Hip.
Let's see what else they say here. So, okay, yeah, they're just working out a lot of the details. It's like, they're trying to parameterize, right? They're trying to say what is going to give us the biggest bang for the buck. And yeah, kind of interesting. Obviously going to have to study this a little bit more, but as I said, I like to start with the pictures and go from there. All right. So let's see. Percentage of NEOs greater than 140 meters. All right. So there's all of them and there's none of them. And this is, you know, I'm hoping that this isn't 0.1%. Maybe no, that's probably 10%, 20%, 30%. But I don't know. Sometimes these papers need to be reviewed a little better because yeah, I'm not quite sure if that means 0.1%. I mean, that's how I would read that. But on the other hand, this is going from 0 to 1, which is like 0% and 100%. So, I don't know. So, left percent of 22nd magnitude NEOs detected versus time for two telescopes. And okay, I wonder why that looks about the same. I would think that two telescopes would increase this speed by a factor of 2. Okay. Okay, yeah, see here, 83%. So yeah, they've got to work on their labels a little bit because that's extremely uh I mean, that can be completely misinterpreted, right? 81.4, Okay, yeah. So it looks like for sure, right? I mean, this looks about the same. This looks almost about the same. But here, when you have a second scope on the other side of the sun, then you get to that 90% point, right? 5 years after, here and here and here, even 10 years after, you're not quite at 90%. Interesting. Interesting. Kind of cool. Kind of cool. So let's see. Synthetic tracking enables a small telescope to achieve similar sensitivity for moving objects um, as a much larger telescope. The reduction in costs make it possible to consider a constellation of microsats distributed around the sun that avoids the saturation effect that would make it virtually impossible to catalog 90% of the 140-meter NEOs in less than 10 years. Very cool. Interesting. So I think that's pretty cool. That's I mean, I don't know about you, right? But let's stop sharing my screen here. But
Now
I
look
mean,
at the chat. We're in a wrestling hype now.
what's that? We're wrestling. Oh,
Yeah.
cool. Okay. Happened to catch Monday Night Raw. Okay. Oops. Forgot that Bobby can see this.
Wow, Hip and Altalana's been in the WWE and stuff. I hope you both got WWE Network.
There you go. There you go. We've got a bunch of WWE fans here. Cool. That's that. That's okay. You are welcome. Well, cool. So, yeah, I mean, I have an interest in these objects, not only, as a scientist, because they're, you know, interesting and, I mean, fundamentally they are just big rocks, but you know, each of them is unique and you know, scientifically interesting, um, commercially interesting, right? Because they potentially have, you know, material that we could actually use for, you know, construction in space, all of that, you know, and not only construction, but things like water and other volatiles, maybe, right? So very, very cool. And you know, maybe most importantly, um, you know, finding these objects, trying to figure out their orbits, and then trying, you know, to calculate, do any of these have a chance of actually hitting the Earth? Okay, because I mean, it's an absolute fact, right? It's an absolute fact that there are many objects out there that definitely for sure have our name on them, right? I mean, this is going to happen. It's not a matter of if; it's just a matter of when. And so, you know, the sooner that we can, you know, detect these objects and then, you know, do follow up observations so we can figure out their orbits, right? I mean, we we need time. The only way to work out a good orbit is time, right? Um, these um, near Earth objects pretty much have the same orbital period as the Earth, right? I mean, it takes about a year or so, um, mainly because they are more or less the same distance from the Sun. Since they're the same distance, their orbital period is going to be about the same. So, you know, we need to observe these objects for at least several months, right, in order to get a good arc, right, a good, you know, piece of the orbit. So then we can sort of, you know, make a nice fit and figure out what the rest of it is. And once we have that orbit um, very accurately known and measured very precisely, then we can calculate forward, right, and see if or when it's going to hit us. And you know, um, sooner we can do that, the better, because the more time that we have to deal with that kind of situation, the better, right? Because you know, I mean, if um, if we find an object that is going to, you know, there's a 95% chance that it's going to hit Earth in like 100 years, right? Then we have time, right? We have time to do something about it, right? We can give it a little nudge. We can blow it up. We can, you know, whatever we're going to do, right? But if we find an object and it turns out that, you know, we observe it, you know, for a few months and we look at the orbit, it's like, oh wow, you know, this thing's going to hit in 2 months, right? Well, there's practically nothing that can be done. I think, you know, maybe if we had 2 months, we could probably nuke it, right? Maybe, um, but you know, does that really solve the problem? I don't know. You know, I mean, when you blow up an asteroid like that, what you're going to get is a lot of little asteroids, right? So is that better than just one, right? I mean, you also have to consider, right, that there's a 70% chance that that asteroid is going to hit an ocean, um, which isn't necessarily as bad as hitting something on the land, but that's going to create its own problems too in terms of a tsunami, and yeah, depending on the size, who knows what else, right? So yeah, these asteroids are problems, and as I said, for sure, there are asteroids and comets unknown to us at this point, right? Completely unknown, that have our name on them, right? They are going to hit us sometime in the future. Um, and right now, we do not have the means of finding those, right? I mean, there have been a couple that actually the Catalina Sky Survey have found. You know, they've detected these objects, relatively small, right? Meters in size, and hours later they hit the Earth, right? Chelyabinsk was like that. There was another one in, was it in Kenya or something? Where yeah, like 8 or 10 hours before it actually hit us, it was detected. It was found for the first time. It was discovered, and that's I mean, if that object was 10 times that size, um, one, we would probably see it sooner, right? It's bigger. Um, but say, and I don't know if it's a linear relationship here or not, but if we're detecting an object 8 hours before it hits, well, if that object was 10 times larger, would that mean we detect it 80 hours before it hits? Not quite sure if that's a linear thing or not. Um, so yeah, it's right now we're in a uh, uh, just like we're running through a shooting gallery, right? Just and
Like missile command.
yeah, and I mean, every time that we see a meteor, right? That's a little piece of something, smashing into the earth. It's just that there's lots and lots and lots of little pieces of dust, and there aren't so many 100-meter objects, or 1,000-meter objects um, um, there. But uh, there probably are thousands and thousands and thousands of them. So yeah, don't know, don't know. It's right now it's a problem, and you know these folks have an interesting solution in order to detect these things. That's sort of the trick, right? Is detecting them. Once you know they're there, then we can use other telescopes to take a closer look and do all the follow-up observations and everything else. It's finding these things that is pretty tough. uh, so yeah, it's but it sort of sounds like they have an idea, and I really need to read that paper closer, because skimming it like this sort of you know gives us a rough idea, but um, I'd I'd like to dive a little bit more into seeing exactly um, what their plans are there. And the cool thing is that modern rockets, right? I mean, a Falcon 9 um, could launch you know like a constellation of 8 of these, easy, super easy, right? I mean, 16 of them, 20 of them, easy, no problem, and have room to spare. So yeah. All right, well, cool. Look, I'm almost out, and I noticed that it's just a little bit past the hour. So I think I think I'm going to get out of here for now. And yeah, so hope everybody has a great evening, a great day, wherever you are on this spherical planet of ours. And yeah, let's see. I'm looking at the chat here.
You're missing a heck of a lot on the chat.
I know. Well. Actually, I've been watching it. Yeah, yeah, um, yeah. Very very cool. So yeah, there are lots of possibilities. Once we find one of these objects that have a you know we think have a pretty good chance of smashing into us, then we have options, right? We can try to move it. We can try to blow it up. We can, uh, uh, you know, one of the ideas, if we have a long, long, long time, right, is you can actually paint like one side of it, like white, right, and just the solar wind, uh, actually the heating and the cooling will change the orbit of these things, and maybe that's enough, right? So you don't have to go to any extreme. You just have to get just a big bucket of paint, just smash smash it down. So yeah, very very cool. So all right, well I'm gonna get out of here. So if you haven't subscribed yet, make sure to do so. Smash the thumbs up if you so desire. I actually got a thumbs down on yesterday's video. I noticed that, and it's like I just like a reaction. So really, really interesting. I think that's very, very cool. I'm going to go out and see if it's clear, because if it is, I'm going to give my little focal reducer a try. And like I said, maybe I'll live stream. I don't know. So we'll see how it looks out there. All right. Take care, everybody. I will see you in a little less than 23 hours from now. All right. Take care, everybody. Bye.